Good morning. In this class, we are going to see about the introduction of the semiconductor, basic structure of P-N junction, and theory of P-N junction along with the barrier potential. So, let me have the introduction of semiconductor. We know already there are two types of semiconductor, intrinsic and extrinsic semiconductor. Intrinsic it is called as pure form of semiconductor, and extrinsic when we add the impurity atom with the intrinsic semiconductor, you can have the extrinsic semiconductor. Depending upon the impurity type we add, we have two types of extrinsic, that is N type semiconductor and P type semiconductor. When we add the pentavalent impurity, we have the N type semiconductor. So since it is a pentavalent, for each and every atom of the pentavalent, we have the creation of one free electron. So therefore, N type semiconductor, the electrons are the majority carriers and holes are the minority carrier. And similarly, if we add the trivalent impurity with the pure semiconductor, we will have the P type semiconductor, that is positive type, because for each and every trivalent impurity atom we have add, one extra hole will be generated. That's why the holes are the majority carriers in P type and the electrons are the minority carriers in N type. So here when we combine these two type of semiconductors chemically, so when the N-type semiconductor is chemically combined with the P-type semiconductor with the special fabrication technique, we can form the junction which is called as the P-N junction. So such a semiconductor P-N junction forms a popular electronic devices which is called the diodes. It is a two-terminal device. We have positive and negative or anode and cathode depending upon the P-type and N-type terminal. So for P-N junction, P-type there are large number of, in P-type there are large number of holes and in N-type there are large number of electrons. So there will be a concentration gradient or there will be a non-uniform doping in the P-N junction. So the P-N junction can also be called as non-uniformly doped material. So let me have the discussion about the basic structure of P-N junction. So this is the P-N junction structure when we connect the P-type and N-type chemically. So this is the junction point where we have joined the P-type and the N-type at x is equal to 0. So initially, so here there is a holes are majority and here this is a electrons are majority. So we have uniform doping. So both type of charge carriers, that is majority as well as minority, exist in each region. That's why we have taken the uniform doping. And in thermal equilibrium, what is the meaning for thermal equilibrium? The number of majority carriers on both sides and number of minority carriers on both sides will be equal. So the interface between the two regions at x is equal to 0, it is called as the junction or the metallurgical junction. So here on both sides of the junction we have two regions. One is the P-type region and the other one is the N-type region. On P side we have majority carriers as hole, that is represented by Pp, which is nothing but the concentration of holes in P-type, which is depending upon the number of trivalent impurity we have added, that is number of acceptor atom we have added, that is represented by Na here. And Np is a minority charge carrier concentration in P-type, which is given by Ni squared by Na. So this is related to the mass action law, right? So here similarly for N side, so Nn is a majority carrier concentration, that is equivalent to the donor impurity concentration, and Pn is the minority carrier concentration, which can be derived as the Ni squared divided by Nd by using the mass action law. So as electrons are in the majority and holes are minority, in N-type semiconductor, Pn is very less than the concentration of electron, that is Nn. So at junction X, the large number of carrier concentration occur, right? So as the junction is crossed from P-type to N-type, at the junction there is a sudden decrease in the hole concentration or the electron concentration, vice versa. So from P-type to N-type there is a sudden decrease in the hole concentration, from N-type to P-type there is a sudden decrease in the electron concentration. So these change in the carrier concentration at the junction, it is sudden. So there is a step change, right? There is a step change from Pp to Pn while in for holes, and there is a sudden change in Np to Nn in for the electron, which means that If it is Np to Nn means that represent the electron concentration in p type to the electron concentration to the n type. So for electron there is a step change from p type to n type. Similarly for holes there is a sudden step change in the step change from pp to pn, that is p type to n type. So due to this step change, the p-n junction can also be called as step graded p-n junction or abrupt p-n junction. So next we can move to the theory of p-n junction. So as we know, p-n junction can be formed by chemically bonding a p-type semiconductor with a n-type semiconductor to form the junction. So p-type there is a large number of holes and n-type there is a large number of electrons. So overall there is a non-uniform distribution of charge carriers in p-type and n-type, right? So when such non-uniform distribution exists, there is a tendency for the charge carriers to move from higher concentration side to lower concentration side. That we can already see that is a process which is called as diffusion. So in unbiased p-n junction, the majority holes from p side start diffusing to n side. Similarly, the majority carriers of electrons from n side moves to the p side. So in n region, the electrons are majority. Holes diffused from n side recombine with the free electrons, right? So there is a tendency of holes to move from p side to n side. So when it comes to n side, so already we have the majority carriers free electrons in the n side. So the diffused hole will recombine with the free electrons. Thus, due to the additionally positive charged hole, these atoms are in n type become positive immobile ions. Positive immobile ion just near to the junction of n region. A simple case. So whenever there is a movement of holes from p side to n side, so the number of holes that is diffused will combine with the free electron and get cancelled. But we have the majority carrier as electron in n side. So after the recombination, there will be a diffusion of holes from p type to n side that will be form the immobile ion region very near to the junction. Similarly, in p region, the free electron diffused from the n side will combine with the holes in the atoms. So the gaining of additional negative charge free electrons, right, will become a negatively immobile ions just near to the p junction. So this is a diagram which explains the immobile ion formation. So whenever this is the p type, so here holes are diffused from p type to n type here. So these holes will recombine with these electrons which is available in the n region. So because of the additional p-type charges, so all the p-type charges which are all immobile ions are accumulated near the junction. Similarly, whenever there is a diffusion of electron from n-type to p-type, so these electrons will combine with these holes. Additionally, because of the excessive electrons from n side to p side, the extra electrons will become the immobile, and that immobile electrons will be formed near to the junction. So there will be more holes diffused in the n side and large positive charge accumulate near the junction of n side. This positive charge repel the positive charge holes and diffusion of holes stop. What does it mean? So from p side to n side there will be more holes will diffuse, right? More holes will diffuse. So this diffused larger number of holes will stop the flow of electrons from n side to p side. So this positive charge repels the positively charged holes and diffusion of holes stop. Similarly, the large negative charge accumulate near the junction of p side. This large negative charge accumulation in p side stops the negatively charged electrons and diffusion of electron will diffuses. So whenever there is a formation of immobile ions near the junction, after the formation of this immobile ions region, the diffusion of holes from p side to n type and diffusion of electron from n type to p type will be stopped. Thus there exists a wall near the junction with the negative immobile ions on P side, right? So this is the negative immobile on P side, and there will be similarly there will be a positive immobile on N side. So there is no charge carriers in this region because there are immobile ions. There is no flow of charge carrier there and there. So this region is depleted off of charge carrier, and hence it is called as depletion region or depletion layer or space charge region. So depletion layer means it is the accumulation of immobile charge carriers. That is why it's called as depletion region. It is depleted of the carriers, the movable carrier. That's why it is called as depletion region. So under equilibrium condition, the depletion region gets widened up to a point where there is no more electrons or holes can cross the junction. Thus, it acts as the barrier. So under the equilibrium condition, there is a formation of immobile ion layer in between in two sides of the junction. That is negatively immobile ion formed in P and positively immobile ion formed in N. So this layer, that is this wall, will act as the barrier for further flow of or further diffusion of the majority carriers from one side to another side, right? So this will act as the barrier for the charge flow from one side to another side. That's why it is called as barrier. Now, what is the meaning of barrier potential? So we know that the barrier, it consists of the immobile ions. So immobile positive ions on N side and immobile negative ions in the P side. But so we have on two sides of the junction we have two charge carriers, that is positive and negative, right, which will create the electric field, which is called as the barrier potential. So the potential difference across the depletion layer, it is called as the barrier potential or junction potential or built-in potential or cut-in potential, right? It is denoted by Vj. It can also be called as the height of the depletion region, and it is denoted as V0 or V eta. So this barrier potential or the width of this is the width of the barrier or the depletion region, and the electric field which is across this barrier, which is called as the barrier potential. So the barrier potential, depending upon the type of the semiconductor, right, whether it is silicon or germanium, it depends upon the donor impurities added, depends upon the acceptor impurities added, depending upon the temperature, right? So in general, for silicon the barrier potential is 0.6 and for germanium it is 0.2, right? Then what is the meaning of effect of temperature in barrier potential? So we have seen four factors which will decide the barrier potential value. One is the type of semiconductor, and the another one is the impurity atom, whether it is donor or acceptor, and the last one is the temperature. About the effect of temperature in barrier potential, right? So practically the width of the depletion layer is 0.5 to 1 micron. As the temperature increases, the width of the depletion layer will decreases, right? So whenever we increase the temperature, so at room temperature the thermal equilibrium will exist. Whenever we increases the temperature, the depletion layer width will be decreases. That means the effect of or the strength of the barrier will start to reduce. So temperature increases, the barrier potential decreases. That means the temperature and the barrier potential are inversely proportional to each other. So the barrier potential decreases approximately 2.5 millivolt per degree Celsius rise in the temperature. This is a constant value approximately. So 2.5 millivolt per degree Celsius rises in temperature. So temperature and depletion layer will be inversely proportional to the